Well, I think we can start. Welcome back, folks. So we're finally to week 15. This is the pivotal week. We're finishing off all of the course content. We're in the last example of the last set of notes, 15.4. So we've pretty much completed everything on the syllabus as well. After we finish this problem here, we're going to jump down to this document, final exam review. This is just an extra collection of more statistical problems. Starts off with the hard questions first, so we can make sure we address those. And then the other interesting questions as well that we took a look at in the course, things like, say, rules of thumbs for outliers, box plots, regression analysis, all those other concepts are also in these notes as well. So that's pretty much our plan so far. We're going to finish up the last section. Quiz number 11 is the last quiz of the entire semester. And from 1 week from today, we'll be in the final exam. Any questions at all, folks, to start us out today before we go through the rest of those announcements? Okay, well, I do have one extra credit opportunity that I want to talk about. This extra credit opportunity is kind of like a fairness as it relates to exams. If you ever had a bad exam in a class, but you came back on the final exam, you might have felt like that should have kind of undone some of the work below here. And that's how my extra credit opportunity works. So it says if your final exam grade is higher than the minimum grade among exams 1, 2, and 3, the final exam grade will replace that minimum grade. And the way it could look is, let's just say for your exams 1, 2, and 3, just as a random example, this is nobody in particular. Let's say the grades came out as 89 for exam 1. Maybe for exam 2, that one was 73. Let's say that was a hard one. And exam 3 was maybe 92. If the final exam grade comes out as, let's just say, a random 85, then this extra credit opportunity would kick in at that moment. What it'll do is I'll look at the minimum grade. It was 73. The final exam grade is higher at 85. So I'll kick that out and put in place 85 instead. So that's the way that extra credit opportunity works. It might not be as exciting if you got, say, hundreds on all of your exams, in which case you're probably just getting an A in the course anyways. But if there's just one problem on any one of those exams that you got tripped up on, then even for that student, this could be an exciting opportunity. Any questions about it at the moment? Okay, and just for extra clarity, this is an extra credit opportunity that will only help, it can't hurt you. So say, for example, maybe you just had a really bad day on the final exam and it was at 72%. That means nothing changes here. I'm not going to drop your minimum exam score down to a 72. You keep all those scores originally, and then that's just your new final exam grade. As far as the grading goes in the semester, a course grade has been published on your return exam 1, exam 2, exam 3 grade. It's basically your course grade that you could look up right now in the Canvas system. And here's how it's calculated. We looked at this on day 1, but we're getting close to the end, so it's good to have a refresher. The way the final exam grade is calculated is it'll be worth 30% of the entire course score. It sounds like a lot, but the final exam is really just things you've seen before, exams 1, 2, and 3. And the review notes we're going to take a look into will be very similar problems as well. If you look over all of your quiz questions, those are meant to be similar final exam questions. And if any of your quiz questions are missing, I'll still accept them for full credit all the way up to Monday, the day of the final exam. Same for homework. This is the MyLab statistics homework. If there's any section that's kind of missing there, you can still redo those sections to get full credit all the way to a final turn-in date. This is essentially the other extra credit opportunity. The final date is going to be Monday, December 15th. So I'll accept any late work, whether it's on a quiz or MyLab statistics, up to, say, 11:59 p.m. on that day. That's when all grades become final, and I'm just grading at that point after that moment. So those are a couple quick extra credit opportunities. And as far as the final exam goes, I think we've mentioned this before. It's not meant to be the world's most nastiest exam. Essentially, with the grade you have right now in this course so far, the final exam grade can only help through this extra credits opportunity. And one thing I do on the final exam is that's the one exam that I might curve depending on how that one goes. I look into the entire class average before the final exam. I see what changes after the final exam, and I let that inform me how much I'll curve the actual final exam. I'm trying to return back to, say, 0. So if this was a tough final exam and the whole class's average grade, computed this way through the syllabus here, the whole class's average grade, say, went down 5%, that tells me it was a tough final exam, and I'm probably going to curve it to bring the average grade back to 0. So that's the one exam that can get curved. And if it does get curved, in this extra credit opportunity, it's the curved grade that replaces the minimum, since that just sounds like the fair thing to do in that case. But that's pretty much it for the extra credit opportunities. Down below here is the same stuff that we've seen before. This is same set of documents, but now it's completed all the way to section 15.4 on version 1, version 2. One of these, I forget which, is just my blank lecture notes. The other one is supposed to be additional problems, but we found some duplicates in there. Got to go through those again. And this is the real final exam that I gave the class a year ago from essentially today. We're going to go over separate problems because I feel like this is such an important student resource. I wouldn't want to spoil it by doing it myself in class. The best way to really use this resource, because it's a real exam, is to try to, say, set aside 2 hours in your busy schedule. I know that's hard, but if you can set aside 2 hours, or maybe just with timers, say you can put in 45 minutes here and 45 minutes there. If you can set some time aside, do this sample final exam as if it's a real exam, like a final exam dress rehearsal, but just mentally tell yourself, this is it, this is the real final. You're not going to look into any other resources other than the 2-page of notes that you're allowed to bring in your TID4 calculator, and just work that exam in the 2-hour set window, and it will give you a very, very honest idea of where you are at with this material, what sections you need to take another look into, things that you might want to study. It might inform you what you need to put in your note card. Maybe something's missing that you detected. Oh, darn it, I needed the confidence interval formula for quantitative data. Something like that could come up. And after that's done, I have the solutions posted here so you can grade yourself as well. Another student in class asked if they could just hand it to me and I could grade for them, and that'd be terrific as well. You can send me in this exam, say like as just an extra assignment that isn't worth a grade. I'll be happy to mark it up for you, let you know how you're doing if I was grading it as a real final exam. Well, I think that's all of my announcements for today. That was a lot of them, 8 minutes worth. But any questions at all before we get started? Okay, we'll talk a little bit more about the final exam on Wednesday as we're reviewing for it, and definitely on Thursday, our last official entire lecture for the semester. But for the moment, let's see, where are we at? We're in 15.4, so we'll finish off this section. And quiz number 11 is really just based off one of these. Hang on. No, quiz number 11 is based off section 15.3 rather. So this is one section that did not have a quiz attached to it. So let's jump back in. First, as usual, just the refresher, here are all the formulas that we're about to work through. To do this confidence interval, or excuse me, hypothesis test procedure, because we're dealing with quantitative data, we calculate a different test statistic t. We're measuring the distance between our data, y bar, and the statement you make in the null hypothesis that mu equals mu naught in terms of not exact standard deviations this time, like with categorical data, but approximate standard deviations. This time it's the standard error, the best tool we have to approximate. So it'll be calculated in this way because there's already an error in estimating a different parameter, the population standard deviation, the y bar. We're now in the t distribution. But all these graphs we found are essentially copy and paste what we saw in the prior section, 15.3, for categorical data. The conclusions we make are identical, whether you put categorical parameter p or the quantitative parameter mu. We're looking for a small p-value before we reject. And the conclusions always go, we either found evidence HA is true, or we fail to find significant statistical evidence, HA, whatever that statement is true. And so these are the decisions or conclusions that we make. Well, after that wrap up, here's our new scenario. Looks like something with environmental sciences. I can't recall if we've seen these data before, but we certainly haven't done a hypothesis test on these data. So it'll be like a new problem in a certain sense. So here's how it starts off. It says, acid rain from the burning of fossil fuels has caused many of the lakes around the world to become acidic. That sets the tone of the major context. The biology in these lakes often collapses because of the rapid unfavorable changes in water chemistry. So acid rain is causing acidic lakes, which is not great for all biology in lakes. And we're told a lake is classified as non-acidic if it has a pH greater than 6. Kind of a weird way that this has been worded, because it seems like the problem is for acidic lakes. They give us something on non-acidic, basic. So let's reword this. Let's say, in other words, acidic if less than, or maybe say equal to 6, a pH of 6. So here's the next thing that happens. Here's the refined context. We have a study, we have some raw data. So these gentlemen, A. Marchetto and A. Lamy, measured the pH of high mountain lakes in the Southern Alps and reported their findings in that paper. Now, I think we looked into this data once before, but I don't think we did anything too heavy with statistical inference. This is maybe just looking at a histogram. So here's pH of high mountain lakes, specifically in the Southern Alps. pH levels were obtained by the researchers in a random sample of 15 lakes. So those are the 15 observations. 1, 2, 3, 4, 5, just double checking now. That looks like 15. So we have a sample size of 15 observations, all pH values. A question is being asked at the 5% significance level, so that's alpha, at 0.05. And that loops back on this alpha here, that we'll use that as our benchmark for obtaining enough evidence for statistical significance. So when it says 5% significance level, we have to know that's the alpha value they're referring to. And here's the question. So this is essentially the alternative hypothesis, this entire statement right here. So everything highlighted there, that's HA. Does the data provide sufficient evidence to conclude that, on average, high mountain lakes in the Southern Alps have a pH different from 6.35? Okay, well, we can say for sure when they said different from, that's a particular kind of test that's implying a not equals. We might have assumed based off this that they're testing for acidity. That would have said less than 6 if they're testing for acidity. But no, they asked a very, very specific question. Is it different from 6.35? We'd have to ask the biologists, the experts, why that number, and they could probably tell us why, but that's what our statistical test is going to be. Different from means not equals, so this is going to be two-tailed. And notice the other thing that's a pattern break from what we've seen. When I looked at that 6 initially, it looks like the value to be tested, mu naught, the hypothesized value rather, but it's not. We're testing if it's specifically different from 6.35. The hypothesized value mu naught is that number then. Mu naught is 6.35 in pH. This has a really particular unit, so I'm kind of paraphrasing by saying unit as a pH, but I think that works just fine for a quick description of the unit in this context. Well, that's the statement of the problem so far. Notice what we're missing though. This has come up before with confidence intervals. This can come up on the real final exam in particular. Not a guarantee, but it's a possibility. Yeah, we don't have. Exactly. Those are the two things we're missing for sure. Looks like everything else we have is apparent here to run the full test. But once we get those in the calculator, we'll be all set. So it's a final exam review question already. This is something that you can almost guarantee will do at least somewhere, at least once, somewhere on the final exam. So hit power on to get summary statistics, hit the stat key, and immediately just hit enter right on the edit field. You might have L1 and L2 both filled out, but we're only going to access L1. Either way, it might be comforting to just clear both, less mental noise that way. I'll type these in going column-wise, left to right. It's good to go slow to just be accurate, but this is a high stakes problem in my lab statistics because we have to get every number dead on right. But if you make a mistake here, but you tell me exactly what your Y bar is and what your S is, you still get partial credit for those values. So just tell me what they came out as. If one's off, you might lose a point, but use those values correctly throughout the rest of the problem and you don't get dinged over and over again. Okay, got a little distracted there. So I have 15 observations. L116 is blank as a double check. Anyone need any additional time? Yeah, this is always a little bit iffy for sure. It's one of those things where the mantra is go slow so you can save time. And it never seems to make sense until it happens. So next thing we hit is stat button again. Move over to calculate one variable statistics. You should see L1 flashing. Hit enter. And if you see a 6.6 and a 0.671, then we probably all put the numbers in identically. Does that look about right to everyone? Awesome. So our calculator uses X bar. Our textbook uses Y bar. The country is kind of split in the middle for statistical textbooks, what to call it. Now next, recall you have to use SX there, the actual standard deviation. So that's 6 point. Let's see, what would be good to round this to? Ask for standard error to 4 decimal places. Let's keep this one to 4 decimal places. So a 0.6719. Let me double check the rounding there. Okay, so I think we've got some statistics. Now the whole problem can start at this point in earnest. First thing we do, this is kind of broken up more than the last section notes. The last section I did parameter, null, and alternative hypothesis in one go, but for some reason I broke it up more in this section. Sorry for that weird noise there. So first for part A, we describe mu. Mu fits because if there's an average in this problem, that means quantitative data. And so mu is measuring the population mean. So mu is the population mean. Or you could say average like we mentioned. But when it comes to quantitative data, this is particular just like categorical data. In categorical data, you have to say what were the successes. You have to mention what's the population. Here, we don't have successes, failures, but we have a unit. So when we say mean, you have to say mean of what specifically? It's the mean pH for all. So that's the first thing we have to worry about. It has to say mean. It cannot say proportion. It has to mention what the data is about, what the unit is. Finally, it has to say what is the population. We can't say for all lakes because we're not talking about all lakes on the planet. We can't say all high mountain lakes because we're also not just talking about all high mountain lakes on the planet. Exactly. We have to really laser focus to high mountain lakes in southern Alps. So that's really highly specific. It was only these lakes that fell into the sample. That implies immediately that's the only sensible population. We can't extrapolate this to every high mountain lake across the entire planet, and certainly not all lakes. So this is the population. So going back to the parameter, we use the population mean pH for all high mountain lakes in, if you said just the Alps, that's tempting. I'm almost out of paper. I think that'd be just fine. But let's go with in the southern Alps. I don't know if that's redundant. I don't know if every lake in the Alps is high mountain, but we're specific now, southern Alps. So after that's done, we can state the null alternative in terms of that parameter. Any questions at all first, folks, getting mu down on paper? Okay, again, it's tricky because when it said, using the context of this study, we had to say mean somewhere. We had to mention the unit pH, and we had to mention the population. This is a really dense sentence we wrote out. The context was really falls apart if we miss any one of those three things. You should say population when you mention that because that tells us it's a parameter. You should use the symbol mu, but these are the major things I'd be looking for, say, grading it on partial credit, those components. Now for null and alternative, let's say we're going to test H naught. Mu takes on some value. Let's put in some space for a blank against HA mu, but we know this is a two-tail test, so this is going to be mu not equal to, leave a little bit more space to complete the sentence, and we'll say at alpha equals 0.05. It's kind of nice to have it in one line. You don't have to put in the words test, against, at, but having all three, including alpha, is a good idea because your eye centers back to this when you go to make the decision. Leaving it off, though, is not a big deal if you chose to. The last thing we fill in, though, is this part, the hypothesized value, mu naught, the same value that's up here at the very top, the null and alternative, is 6.35. So that's finally all the little components of the hypothesis test put down once we get to this last step here. The rest of the problem is using formulas, using the sample statistics, sample size, and the calculator to get our p-value out. So we can return back to this table and check if our p-value is small enough so that we can reject the null and say we have conclusion of whatever this alternative is. We'll have to write it out in ordinary words again.
Are you gonna wanna see the pH, the label of the unit on those or not?
You know, that's a good question. I think it would have been better with a pH, but I wouldn't be too picky if you did decide to leave them off. But because you mentioned that, let's actually put them on for the sake of the course notes. I think when it comes to quantitative data, the more often you do put in the units, including your hypotheses, the easier it is to interpret the problem, the main conclusion at the very end. So thanks for asking about that. Other questions so far? Okay, well, this is broken down a lot. So next part, degrees of freedom, which we summarize to DF, sample size n minus 1, but that just means it's 15 minus 1. So degrees of freedom is 14. Probably the nicest, most friendliest formula in the entire course is that one there. Once we have degrees of freedom, now we're ready for the standard error. But the standard error is not bad either. When it comes to quantitative data, this is always the same object. You might call it SCY bar to connect the dots with how the formulas are written down. Main thing you'll calculate is S divided by square root of sample size n. So now we're making two substitutions. S we computed and rounded to those 4 decimal places. 0.6719. Divide by square root, which we found to be 15. So we drop that in its container down here. This one says specifically round to 4 decimal places. So we'll follow that to the letter. 0.6719 divide by square root of 15. So to 4 decimal places, this one will round up to a 0.1735. Well, the next thing is the test statistic. Here's where we see how far is our data in terms of the sample mean y bar from the hypothesized value, the 6.35 pH. We're above, we're on the non-acidic side, it looks like. That's kind of interesting. Acidic if it's less than 6, a pH of 6. But you know, these are high mountain lakes. Maybe they're just not as affected by acid rain. These are definitely not even on the acidic side at all, 6.6. So the test statistic is just another formula. We have everything that we need to compute it. It goes like this. First, it's a good call to write down the formula to organize our thoughts. Let our subconscious chew on it for a moment. It's y bar minus mu naught. Divide by the standard error, the thing we just computed. Standard error of y bar. Okay, so let's drop in those values. Scroll to the point where I can still see the 6.6 for y bar. It's way up here. Subtract the value mu, 6.35. Standard deviation is pretty small, 0.1735. But is it small enough for statistical inference? I have no idea. Let's calculate this. It'll give us a slightly better idea. First, any questions at all, folks? Putting it all together in that formula here. Okay, this finally, again, we mentioned this before. This is the major reason we talked about z-scores in the very first place, all because of hypothesis testing. This is where it comes back. So let's do 6.6 minus 6.35 divide by 0.1735, and that's our standard deviation. You know, that's not a lot of them. 1.5 standard deviations is slightly unusual, but that might not make the cut for statistical inference. Nonetheless, let's write down what we found, 1.4409. Now you don't have to put a unit on this one, but it's good to know that this is in terms of approximate standard deviations. So our data is 1.4409 approximate standard deviations away from that statement in the null hypothesis that the mean is actually a pH of 6.35 instead. So is it statistical inference? Well, that depends. We have to get the p-value out. It doesn't look like it to me, but we have to find the exact p-value to know with complete certainty. Here's where we start going back to what the test was in the very first place. So I'm going to take a screenshot of both parts A and B. Let's put it down here for a quick reference. To get the p-value out, first thing we do is just draw a really fast curve. Here's the t distribution curve. This curve is tricky because it depends on the degrees of freedom, but we computed that already. The df that we found was 14. So I wrote a t df generically, but if all you put in is t14, that'd be a great way to specify it. We have a center 0 here. The test statistic came out positive. So here's our positive 1.4409. First, this is one standard deviation. So that means this is about 2. And t is about here, 1.4409. Our curve isn't perfect. It looks really shoddy, hand-drawn. I'm trying to fix it right now. But really, our main thing here with the curve is just to try to put information together. And if anything goes wrong in your calculator, let's imagine this is a 4-point problem. I would consider this 2 out of the 4 points. This is the major logic, the things that we have to connect together, the test statistic and the right curve. So this is pretty good insurance on getting the right p-value. But here now is the major word of warning on this one. Remember that not equals? That means it's a two-tailed test. That means the area isn't just this area. We also go symmetrically to the left and collect area over here as well. The whole test is now based off this area. We literally use 2 in the two tails. So when we go to calculate our p-value, we will double something. So this is a great way to make sure you don't forget to do that. Put on paper 2 times a value, and then we'll remember to double it when we're in the calculator. At this stage, we're ready for the t-distribution. Forgot to put one thing on the notes. This is an entire TCDF problem in our calculator. That means you'll hit second and vars to access your probability distributions. Skip all the way down to TCDF. Recall you used inverse t to get the critical number t star for confidence intervals, but now we're using TCDF. It wants a lower value. We're going to base it off the test statistic that we found, this one. Let me plug this into the notes just as a reminder. This is input 1, lower, which implies input 2, upper, is 10 power 99. And the degrees of freedom is just that 14 you see right there. So go 1.4409. 10 power 9 is already set. Drop the degrees of freedom down to 14. And that's what the calculator should look like. Hit enter. Let it compute. And never celebrate too early with the two-tail test, because this is half the p-value literally. 0.0858. Then in your calculator, hit times 2. Now we're doubling it. This is the actual p-value. So a two-tailed test always has a p-value that's double either the left tail or the right tail test. That's interesting, and that's also interesting when we say it's the default test at the same exact time. You need specific reasons to change this to a left tail or a right tail. But to 4 decimal places, this is what we have. It's a large p-value. And we're checking it against a significance level alpha at 0.05. So this informs us what we're going to do on the next step. I want to put a box here just to convey that's what the answer would be on this one. But any last questions or comments, folks? Anyone get a slightly different p-value? Okay, reason for the box also is sometimes when you calculate the p-value, you also have another thought that's going on in the back of your mind. The p-value is 0.1716. Now look to this part of the paper right here in part B. The significance level is 0.05. This is bigger than or equal to 0.05, which means the decision we're going to make is we fail to reject HA. Confusingly though, we still go back to HA and we make a conclusion relative to whatever that statement was. We're just going to say we failed to find enough statistical evidence to conclude that that's true. I probably should put it in a box. It makes it seem like that's our answer. But we still go back to that line there. So that's going to be the last thing we do in the notes. I'll leave this here for a reference for what the last step will look like. And we'll put the last step right under part G. we want a practical conclusion. Doesn't hurt to remind ourselves of what we mean by that. This is the conclusion. Lack of evidence, mu not equal 6.35 at 0.05 significance level. But if you tell that to people, you sound like a robot. And now they don't even trust that you did anything right at that point. They're probably not going to trust your results. So we have to say this in a way that flows, that people will understand. That's what we mean by the practical conclusion. We have to mention the study. That's what we mean by the context. But if we just follow this as a guide, we kind of already know what this is going to look like. First, let's focus on the fail to reject. This means we have not found, combine those two, yeah, not found. I thought you were referring to that F that I put there.
No.
Yeah, we have not found enough not found enough statistical evidence. So that's a great way to start it out in this case. If you didn't mention 0.05 for the significance level, I wouldn't hold that against you. I personally find that it's weird to leave it off. That's why for every hypothesis test, I put it in parentheses to say it's optional. But I think it's just a good way to be honest, kind of like with confidence intervals, mentioning the confidence level. It's curious that that's more standard than it is mentioning the significance level. So I'll put it here in parentheses at the 5% level of significance. There's a downside to this. The downside is if you tell people at the 5% level of significance, you might have to explain that. You can say that's the benchmark for finding significant evidence. But then they might ask you, in what way is that a benchmark? And that's when it can get a little bit complicated. That's the downside of mentioning it. But on to the next part. We have not found enough significant statistical evidence at that level that this is true. So we'll just read out verbatim as we see it that the population mean pH for all high mountain lakes in the Southern Alps Okay, so that amount of writing was just mu. We can now put in verbatim if we'd like, is different from, or you might have said is not equals to, anything along those lines that conveys the not equal direction would work. And then we just say 6.35. We already mentioned the unit, so we can just put a period right on that. And that's the conclusion we gave. A lack of evidence for this statement here, the alternative hypothesis. So any which way this goes, we always return to that original alternative hypothesis, which makes sense. It's the research question. The null hypothesis just had to tell us, how are we getting our test statistic? What is the de facto assumption? What's the statement of no change? What's the statement of not guilty, essentially, in this problem? But the research question is encapsulated here. That's why for every hypothesis test we've ran, we always return to HA, no matter what the p-value came out as. But we did it, folks. That is the last problem of the last section for the entire course. We were way behind. We might have not had a review, but now we have a couple days. Yeah, go ahead. I would say so, but the reason I haven't been putting it down below here is when it's referring to the practical conclusion, it's really just referring to this whole part right here. So if you said above, we fail to reject H naught, I would say that's a good thing to put into part G, but you would still have to say something along these lines down below. Oh, I see what you're saying. You could say, you're saying that we could write out a conclusion that goes, we failed to reject that mu equals 6.35 and then just say the rest of it, but say what mu is. I would say that that's an okay conclusion to make, but it does come with one tiny, tiny danger. When you write that out, when you say this study has failed to reject that mu equals 6.35, the miscommunication that might occur, unless we're really touchy with how we write that up, is people might read your words and think what you're saying is the null hypothesis is true, that our study found evidence the null is true. So just have to be really careful. You stay away from any language that can convey that. So if you said it just the way you said it, that would be perfectly fine. And I would read that in for a full credit response. The way it gets tricky is the mistake that often is made is people sometimes say, we have found evidence that the population mean pH for all high mountain lakes is 6.35 because we didn't reject the null. That would be the only time we would lose credit in that case. So as long as you're avoiding that statement, yeah, you can absolutely say it that way. Other questions at the moment? Okay, well, we did it, folks. Let's save this up. I have a pretty big review, so I'm kind of excited that we have like 2.5 days. So even though it didn't seem like we were working kind of fast, I think we actually went a little bit faster than we might have thought. I'll kind of chalk that up to smaller classes. Sometimes a smaller class just doesn't have as many questions as, say, a really big class. This class size was originally like 22 until the reality of the late hours actually hit everybody and people started changing up their schedule before we started. But with where we're at now, we're returning to this document. Well, not returning to, we're starting this document, the final exam review. Before I start this document, I want to show you one thing I haven't really talked about just yet that does happen in this class, which is a little bit weird and frustrating sometimes. This final exam here is the real one that I wrote, almost. There's a change on there. And you can definitely see that change when you look in the solutions. These are the actual solutions to every single problem, the way the real exam actually look. So this class, statistical reasoning 1153, is coordinated by the math department. And you saw one person assessing this class once. That's not the person in here today. That's Abby, who's here with us. No one is actually assessing this class. But they do one extra assessment at the end of the class on a course concept. The assessment this year is on inferential statistics, which means the math department has taken two problems on the exam, which I like to write personally, and they wrote their own problems. They've changed the instructions entirely to the way I like to write my questions, which is unfortunate and jarring. So we'll make a pretty big deal out of this, especially on Thursday, when I give you advice on writing your 2 pages of notes for the final exam. The actual question looks a little different. The problem is not bad. It's a standard problem like the ones that we've done in class. I've seen the question they're asking on the final, but this is what the question looks like. Perform the appropriate hypothesis test at a certain alpha level. And that's not the worst thing in the world, but that's tough to do when you're still just learning this content. The way I actually wrote that question looked like this. I broke it down like the way we're used to seeing in the notes. It looks like I made a typo there as well. I said population characteristic, the old book, and I should have said parameter. I've cleaned up that typo. But I like asking the parts A, forgot part P, C, D, E, and F. I like to break down the problems like that. But they didn't do that for us. They're just asking you, do the test, and then just move on. So we'll have to navigate that as we review our problems. How do you run this out when there's no guidance? You're just told it's a test. We'll make that a big part of our review. And for the other one was the confidence interval, where part A is construct and interpret a confidence interval. I broke that down into like parts A through G, basically, like we're used to seeing. And a follow-up question. We did one like this in class as well, so we'll focus on what a follow-up question could look like as well. But my main complaint, the instructions changed, is this. We'll see a conference interval question that looks like this on a real final exam. This is going to be the last two questions. I can't say which one's which because we have to decide that when we see the exam. The last two questions are written by the math department in this kind of funky, huge amount of white space sort of way, which again, it's not a bad way to ask the question, but it does make it a little bit tougher. So that's a big part of our review, just kind of a heads up on the change the way the exam's written. So now when we open up those review questions, to make this an effective review, I did the same thing. Perform the hypothesis test showing all steps. The department didn't even say this part, put in the practical conclusion. It's implied. We're supposed to do that every time we do a hypothesis test. I just made that more apparent on the notes here. So this is the review of statistical inference methods. I have 1, 2, 3, 4 examples. I do need one example that has a follow-up question. Let me make a quick reminder.
I think there was a question in my lab statistics that was kind of like that. It doesn't walk you through all of the little.
Yeah.
steps.
There's a couple just like that. I agree. They like the follow-up steps are just like the extra hard concept questions, basically, is what the follow-up stuff was. But my reminder is going to be add a follow-up question to the confidence interval problem, making it even more similar to what we're seeing on our real final exam. So after we get through those 4 problems on statistical inference, that's the hard part of the review. I'll go into other problems. So our final exam, I think I said it's 8 questions. It's already written. It's between 8 or 9. I don't exactly remember the complete number.
Well,
Oh, it's been reduced then. Definitely down from 12 to between 8 and 9 questions. So it's going to be like 2 exams just basically glommed together. Exams are typically 3 to 4 questions. These are the other problems that are going to be asked. Box plot type problems, Z-score type problems. This is a regression analysis type question. You should expect this on the real final exam as well. Looks like just a routine normal distribution question. So that's what our full review is going to look like. I also want to mention to the class, if there's another problem that you would like to see solved, not on these notes, from anywhere else, old exam questions, a problem from my lab statistics, an old quiz problem, let me know at any point during this review, today, Wednesday, or Thursday, and I'll be happy to get into those. Yeah. Yes, it can. So any chapter whatsoever. It's going to be overwhelming when we think in those terms because there's a lot of chapters we covered, right? So one big hint on what I do for my final exams is I also check my quizzes. What were the quizzes that we actually asked in the class? I check my notes and I check the MyLab statistics homework. But for say like this chapter right here, relationships between categorical variables, if I look at this chapter, it was kind of confusing. This one came in as an actual exam question. And there's certain things that we talked about, but we never actually returned to, like, for example, independent categorical variables versus dependent. This was important stuff, but because we never came back to that, wasn't on quiz 3. I'm not sure if I remember what quiz 3 even was. We're going to find out real quick here. Quiz 3 was a whole different problem. You probably would expect the chapter 3 problem to be more basic, something like you saw in exam 1. This stuff never came into a quiz, so this is not going to be on a final exam. That's one additional kind of like a proofread check I do when I write the final exam. It's off any chapter, but it's going to be the concepts that we really emphasized. And the quiz itself is a strong emphasis in a certain sense. It being on the exam as well is a second level of strong emphasis. So review your quizzes, review your exams, and you'll get a very good idea of what's really on the final exam. Even though it's completely comprehensive, every chapter is open. I'm not going to ask questions that we didn't spend very much time really working on. Other questions about that so far? Okay, yeah, go ahead. That's a great question. I think it's going to be pretty balanced, actually. There'll be one hypothesis test question, one confidence interval question, but really we were doing hypothesis testing and confidence intervals probably since, I forget, it's been a while, hasn't it? We started all that stuff in, it was still October, all the way to November. So really from this week 10 all the way to week 15, two questions, hypothesis test or a confidence interval. So I would say the last 5 weeks is actually kind of more spread out. And then the rest of the 10 weeks is going to be pretty spread out as well. But this was the hard part of the course, statistical inference. And so this isn't majorly emphasized. It's going to be pretty generous, I would say, on our final. Other questions at the moment? Okay, well, let's give this a try. I think we have enough time to start this problem, start talking about the strategies that you'd want to put down on notes. If you see a question like this, and you will on the final exam, first let's read through the context and see what it's even all about. Most Like It Hot is the title of a press release by the Pew Research Center in 2009. The press release states that by an overwhelming margin, Americans want to live in a sunny place. That sounds right for this time of year, sometimes in Idaho. This statement is based on data from a nationally representative sample of 2,260 adult Americans. So we've got the sample size at least, 2260. Now, if this was a real exam, I probably would be penning this right here, right in the margin, to start kind of organizing our thoughts on this. Okay, so out of 2,260 Americans, it says, of those surveyed, 1,288 indicated that they would prefer to live in a hot climate rather than a cold climate. Now, you know what's came up quite twice is wanting to live in a hot climate. Would you agree that this is starting to look like categorical data, success failure type outcomes? Awesome. There's no units here. There's no inches, miles. The last problem that we just took a look into, what was that one? That was pH for the unit. But this one just has preferring to live in a hot climate or not. So when it says 1,208 who prefer to live in a hot climate, that's definitely underline worthy or highlighter worthy if you brought a highlighter. I would say 1,288 successes are in this sample. So the moment you said successes, this also tells us our data is categorical, which tells us the parameter. Absolutely, good call. This is going to be population's proportion of successes. Now, next thing it says, suppose you want to determine if there's convincing evidence that a majority of all Americans prefer a hot climate over a cold climate. That's a weird statement, just suppose that. Then it launches in, perform a hypothesis test showing all steps, provide a practical conclusion using the context. Well, this wasn't a question, but you could kind of form it as a question. You could turn this, which is almost a demand, into, is there convincing evidence that a majority of all Americans prefer a hot climate over a cold climate? Question mark. It's essentially the alternative hypothesis, this entire statement. It makes sense because we're looking for a hypothesis if they say hypothesis test. They don't always have a question mark, so sometimes we have to hunt for what would fit. But this is what we're looking for. Let's determine the direction of a test, though. If there's convincing evidence that a majority of all Americans prefer a hot climate over a cold climate. I hate this wording here. This is pretty overloaded. A majority says more than 50%. And I think this would make it an exceptionally tough exam question because there's a lot baked into just one word this time. But that's why we're reviewing this here for when these kind of things happen. If this was on our real final exam, I would probably give a hint to the class because I would feel that that's just kind of unfair in an exam setting to suss out all this extra information. Because more than is also conveying greater than, it's a right-tailed test. And when they said majority, they also gave us that P naught is 0.50 at the same time. Basically, everything you need to really get going on this test is in one word, majority. Majority simply to be taken more than 50%, giving us the hypothesized value at the same exact time. Well, that's a tough question, but the next thing that's tough is the instructions are not really what we've been doing in class. So this is kind of a higher level of a problem if we have to do everything from scratch. This is where your notes are probably going to be really, really helpful. So you have 2 pages of notes. It wouldn't be a bad idea to dedicate of those 4 pages front and back, 1.5 even to just the statistical inferences. Hypothesis testing and confidence intervals would be a good idea. Maybe even one of those 2 pages front and back could be dedicated to this. If I was going to write down the hypothesis test as a step-by-step guide, I would probably make this my step 1. Hang on. You know, the problem in the actual exam is also going to tell us our significance level alpha. You might not have spotted it. I don't see it either. Let's change instructions just a little bit. The test in the real exam is going to say, showing all steps, using a, let's go generic, 5% level of significance. So sorry for that quick change there. And now my box here is not fitting quite right. That word majority is kind of tricky. Alpha here is 0.05. Okay, really my step 1 should be make sure you really read through that context. Maybe read it through it a couple times. This is a 2-hour final exam, but extra time has been committed to make sure you have extra time to really read the context and check your work. And this is part of that. Now, on a step-by-step guide, here is a highly recommended step 1. Parameter and hypotheses. So let's start out with the parameter, mu. And this is kind of jarring because remember in the last problem we just did, we said population mean. That doesn't fit here. The parameter is P, we have to do population proportion, and those words do matter. When we define the parameter, we'll say mu equals the population proportion. Oh, that should be a P equals. Thanks for mentioning that. That would have been a mistake for sure. Mu should be the population mean, the one that we were just doing, but it's actually a P. Thanks for spotting that. P equals the population proportion. The word proportion is important here. If you make a mistake on the symbol like I just did, I'd probably just pen in P instead of mu, but I wouldn't take off a point on that level. P is going to be the population proportion of successes, but that's just people indicating they would prefer to live in a hot climate. So we could say population proportion of people. I'll paraphrase it by losing the word indicated. I'll just say people who prefer to live in a hot climate. And we have to say among what population? Well, it looks like it's just USA citizens. They said Americans, and they said it was a nationally representative sample of 2,260 Americans. So it looks like we're just talking about everyone in the USA. Excuse me. So let's say among all USA citizens. Or just paraphrase that to among all Americans, and that should work as well. The context will reframe that as we're probably talking about the USA specifically. And that population is important because if this was just people living in, say, Idaho, or just people living in Canada, the study might have gone a lot differently. Who knows? So there's the parameter. Next thing is hypotheses. So let's test H naught. Mu equals, let's just plug in the hypothesized value. We've seen this put together before. Yeah, it absolutely is. Thanks for spotting that. That last problem is just keeping my muscle memory down on the mu, it looks like. So P equals for the categorical data against HA. I think I've got this one. P equals, thanks for again for spotting those. Except it's a not an equal on this one. This is a greater than for the right tail test. So HA is that P is greater than a 0.50, same value as before, at alpha equals 0.05. So this whole problem is just one entirely whited out page. So you have the real estate to write out all this stuff. Step 2 is not the condition checking. So for the final exam, we're not going to ask you to run through the conditions. They would have to ask you a specific question. I would have to ask you a whole different question for the condition checking. That's what we did on the exam as well. When the condition checking came up, it was a whole separate problem. So for our step 2, the next thing we're going to look into is test statistic. And then for our next step, it'll be the p-value. So let's say for step 2, compute test statistic Z. Good strategy here is just to write it down as a formula. Z equals p hat minus p naught, divide by standard deviation. Excuse me, yeah, standard deviation, got those mixed up for just a second there. Standard deviation of p hat. In our last notes, it was the standard error, but categorical data goes differently for their test statistic. And we kind of have some of this information already. We never computed p hat, but it's looking at us. These are the two halves. That's the numerator, that's the denominator. So let's compute it right here on paper. P hat is 1288. There's no point yet. Divide by 2260. They didn't say anything about rounding on this problem, so I'm not going to be picky about it either. Let's round this to 4 decimal places and call that okay. As a MyLab statistics problem, though, probably keep this to 6 decimal places, just for the sake of accuracy. They're really picky in this one section. So 1288 divide by 2260 gives us 0.5699. So almost 57% of the sample said they would prefer to live in a hot climate. That's definitely more than 50%. Sorry, question? Yeah. I think that'd be a great assumption. Yeah, that works out great for the test statistic, the p-values. So 4 decimal places is a great way to go, even in conference interval problems as well. Other questions at the moment? Okay, let's write out the denominator, the last thing that's missing. Standard deviation of p hat is tricky. This is the one where I have a high chance personally of making a mistake, kind of like putting a mu down instead of p. This one is extremely tricky because if it's a confidence interval problem, p hat goes inside here and we call it standard error. But calling it standard deviation is a good reminder that you're actually using this value, p naught, times 1 minus p naught, divide by sample size, n. So we use the hypothesized value to calculate the standard deviation. So that means it's going to be 0.5 times 1 minus 0.5, then divide by sample size n, which is 2260. So there's our standard deviation. We'll hit power 2 button with the second key. We'll 0.5, 1 minus 0.5, which is really just 0.5 squared, but we're putting it down verbatim, divide by 2260. And the number I get to 4 decimal places is a 0.0105. Okay, now we just stitch this all together. Z, the test statistic we want to compute on step 2, is going to be 0.5699 minus the hypothesized value, 0.50, then divide by standard deviation, 0.0105, and we're about ready to compute those standard deviations. So don't forget to parenthesis in the numerator when you're back to the calculator. Go 0.5699 minus 0.50. And a great way to divide by that number, 0.0105, is hit division, up arrow, and hit enter to highlight this and paste it down. Now we're less worried about the places we rounded to. It's going to keep this entire object in before it goes to calculate. And that's a lot of standard deviations. 6.6460. We still need a p-value, but you know what? I could tell you right away, right at this level right here, we have very, very strong statistical evidence, an overwhelming amount, that the alternative hypothesis is actually true, just right at this step. Step 3, we're running out of time on, but it doesn't hurt to put it down on paper, is to do the following. Compute the p-value, and then step 4 will be to give a practical conclusion. Let's write that in just so it's something we can come back to. Step 4, give a practical conclusion using context. So even if you didn't state the parameter p on step 1, I wouldn't dock you on that because there's no part A telling you specifically to do that any longer. But you still would want that in the back of your mind because we absolutely have to put it below in step 4 when we go to give our conclusion. But we're nearly there. Sorry for losing parts A through G like we're used to seeing. That's kind of a random change right at the end of the semester. But if we're prepared for it, if you write out these steps on your notes to see how they would come together, this is basically parts A, B, C, D, and E. We're doing the same kind of work, either way you look at it. Well, any last questions at all, folks, before we end a little bit earlier today? We'll come back to the p-value next.
So we're gonna use the normal CDF, right?
Absolutely. We'll shade to the right of 6.64 with normal CDF, and that'll give it to us, possibly in scientific notation on this one. Yeah, those are always kind of random putting into a system. Well, have a great night, folks. Wednesday's class, we'll just be running through these notes. We'll probably finish off inference on Wednesday or get very close to it. Start doing the other review problems when we come back on Thursday. Now, whatever we don't finish, I'll still put in the full solutions here. So if you have any other questions you want to discuss, don't hesitate to bring them up. It's not going to shorten these notes. We'll still have the full solutions. But have a great night, folks. We'll be back to it Wednesday.
That question, ABC, so that's going to be on the test.
The test is going to look more like Just getting there, one moment. It's gonna look more like these problems that were, oh, that's the wrong one. It's gonna look more like these problems that we were just working on, where there's just the statement. Perform a confidence interval, and that's all it says. So it's gonna look more like those.
Oh,
Unfortunately, it's not my favorite way to ask an exam question, but the math department wrote two of them. And these are gonna be what they look like, the last two questions on the final exam. So basically, one big question and a whole bunch of white space we have to fill in.
so last two questions. So,
Just the last two. The rest of them I wrote. It's the same way you're used to seeing them.
good night, everyone.
See ya.